March 1945. A frozen field outside Bielefeld, western Germany. The bomber did not burn the way it should have. The wreckage lay scattered across hardened mud. Wing fragments snapped cleanly, fuselage torn open, bomb bay twisted into itself. No sign of fuel fire, no evidence of catastrophic explosion, just a machine that had come apart in the air and fallen straight down. A Luftwaffe engineer knelt beside the largest remaining section of engine mount. He brushed away dirt with his glove and the data plate still bolted to the frame. Rolls-Royce Merlin. He froze for a moment, then checked it again. Same designation, same manufacturer, same serial format he had seen dozens of times before on fighters. Spitfires shot down over the channel, Hurricanes pulled from fields in France. Engines that belonged on aircraft a fraction of this size. He looked up at the rest of the wreckage. This had been a heavy bomber. The engineer stood slowly, scanning the debris field. 4 separate engine cradles, 4 propeller hubs, 4 identical mounting patterns. Whatever had brought the aircraft down, it hadn't been a single failure. The bomber had flown long enough for all 4 engines to leave marks across the countryside. Back at headquarters, his report contained a single sentence written twice, once crossed out, then rewritten. Data internally consistent. Configuration contradicts accepted performance limits. He left it at that, no speculation. No conclusion. Because none made sense. For the Luftwaffe, power followed rules. Fighter engines powered fighters. Bombers required engines built for endurance, weight, and sustained output. Transport aircraft had their own designs. Every category existed for a reason. Mixing them invited disaster. German doctrine was built around specialization. The Junkers JM engines powered medium bombers. Radial engines with wide cooling margins handled long patrols and heavy loads. High-performance engines were reserved for fighters, aircraft that lived fast and died fast. This logic had never failed Germany in the early years of the war. So when reports began circulating that British heavy bombers were flying night after night using engines commonly associated with fighters, the assumption was simple: the intelligence was wrong. Captured documents were often incomplete. Wreckage could be. British deception units had fed false data into German channels before. It was far more likely that the Allies were disguising engine types than rewriting the laws of aviation. Air Ministry analysts filed the early reports under clerical error. Then the losses continued. Bombers came down over Hamburg, over the Ruhr, over Berlin. Each wreckage site told the same story, same mounting patterns, same engine configuration, same data plates. The Doctrine Review Board met in late 1943. The conclusion was unanimous. If the British were truly flying heavy bombers with engines intended for much lighter aircraft, those bombers would suffer predictable weaknesses: limited range, high failure rates, instability under load. They would be vulnerable during climb, landing, or engine loss. German night fighters were instructed to watch for these signs. They never saw them. By early 1944, the pattern could no longer be ignored. British bombers were flying deeper into Germany, carrying heavier payloads, returning with loss rates that did not match German projections. Interception reports noted aircraft continuing stable flight, even after sustaining damage that should have forced immediate descent. Night fighter crews began reporting something unusual. Engine failures did not produce the expected behavior. Normally, when a heavy bomber lost power on one side, the aircraft yawed violently. Pilots fought to keep wings level. Many lost control entirely. This was standard, this was taught, this was documented. But these British bombers behaved differently. A night fighter pilot from NJG-1 described an engagement near Kassel. He fired into the starboard wing of a bomber at close range. One engine flared, then went dark. The bomber did not roll. It did not drop altitude. It did not break formation. It continued straight and level, its navigation lights steady, its silhouette unchanged. The pilot assumed a delayed failure. He stayed with the target, waiting for the inevitable loss of control. It never came. Flak batteries reported similar observations. Bombers absorbing damage, shedding components, yet maintaining flight paths long enough to reach their targets. Crews reported no visible struggle at the controls. The behavior contradicted every expectation German crews had been trained on. Intelligence officers attempted to reconcile the reports with known engineering constraints. They reviewed performance charts. They re-examined Allied production data. They calculated power margins using standard assumptions. Nothing matched what pilots were seeing in the sky. By mid-1944, Luftwaffe analysts were forced to admit a disturbing possibility. The British bombers were not surviving by luck. They were surviving by design. But no one could explain how. The rules said it couldn't work. The combat reports said it did. And until those two realities aligned, German air defense remained one step behind an enemy that appeared to be flying machines built on a different set of assumptions. The first explanation came from experience. German pilots had seen this before, at least something like it. American heavy bombers, particularly the B-17, had earned a reputation for staying airborne despite damage that should have destroyed them. Crews spoke of aircraft returning with sections missing, engines shot out, control surfaces shredded. The explanation was simple: overbuilt structures, excess strength, redundancy. So the British bombers were placed in the same category. The hypothesis made sense. British industry under constant bombardment had every incentive to survivability: reinforced spars, extra structural members, conservative safety margins, aircraft built not to be elegant but to endure. Intelligence officers labeled it the fortress effect. If the bomber was simply stronger than expected, then engine failures would matter less. Damage would be absorbed rather than amplified. The aircraft would limp home instead of breaking apart. Night fighter tactics were adjusted accordingly. Pilots were instructed to concentrate fire on the wings, not the fuselage, target fuel tanks, cause fires, force catastrophic failure instead of relying on loss of control. For several weeks, the reports appeared to support the theory. Bombers hit hard did eventually fall. But something still didn't fit. The British aircraft did not behave like fortresses. Fortresses staggered, they wallowed, they bled altitude. They became unstable long before they died. These bombers did not. They remained clean in the air until the moment they didn't exist anymore. No prolonged struggle. No visible fight against physics. They flew as if nothing had changed, until suddenly everything had. The second hypothesis was more technical. If the aircraft was not stronger, then perhaps it was lighter. British aircraft design had a reputation for unconventional materials: wood, fabric, non-strategic alloys. Less metal meant less weight. Less weight meant lower stress when damaged. A lighter bomber could afford to lose power without losing control. This theory spread quickly through intelligence circles. It explained why the bombers could remain stable after damage. It explained their endurance. It explained why they seemed to defy expectations without openly violating them. Reconnaissance units were tasked with confirming it. Wreckage was examined more carefully. Structural fragments were catalogued. Metallurgical samples were taken where possible. The results killed the theory. The aircraft were not unusually light. Wing sections showed standard construction. Load-bearing elements were thick, not thin. Reinforcements were present where one would expect them to be present on any heavy bomber designed for long-range operations. In some cases, the British bombers were heavier than their German equivalents. This was the moment when frustration began to creep into the reports. German analysts tried a third explanation: pilot skill. Perhaps British crews were simply better trained at handling asymmetric thrust. Perhaps their procedures allowed them to keep aircraft under control longer. Perhaps what German pilots interpreted as stability was actually disciplined compensation at the controls. The idea failed under scrutiny. Night engagements left no time for finesse. Damage occurred suddenly, often catastrophically. And yet the aircraft did not react the way physics said it should, even briefly. No amount of pilot skill could eliminate the yaw produced by a major power imbalance. No training manual could override aerodynamic reality. By late 1944, the language and intelligence summaries changed. Words like unexpected and unusual gave way to unexplained. One report ended with a sentence that stood out among pages of measured analysis. Observed performance cannot be reconciled with current models. At that point, the Luftwaffe stopped trying to explain the behavior in advance. They began reacting to it instead. Interceptors were instructed to attack in pairs. Flak concentrations were increased. Engagement envelopes were tightened. None of it addressed the underlying problem. The bombers were not winning by speed alone. They were not surviving by strength alone. They were not defying gravity by accident. They were operating according to a logic German engineers had not accounted for. And until that logic was understood, every calculation remained incomplete. The breakthrough did not come from the sky. It came from a desk. Late in 1944, a junior analyst in the Reich Aviation Ministry was tasked with reconciling bomber loss reports with structural failure data. His assignment was simple: explain why British bombers were remaining controllable after damage that should have made them. He started where everyone else had started. Power. How much thrust the aircraft had. How much weight it carried. What should happen when one side stopped producing force? The numbers did not work. So he stopped treating the aircraft as a collection of parts and began treating it as a system. That was the first mistake German doctrine had made. German engineering emphasized specialization and optimization. Each component was designed for peak performance in a narrowly defined role. Engines were evaluated individually. Wings were evaluated independently. Structural strength was calculated in isolation. But the British bomber did not behave like isolated components bolted together. It behaved like a balanced mechanism. The analyst focused on one detail that had been consistently overlooked. Damage reports showed engines failing without triggering immediate loss of control, not delayed loss, not partial loss. No loss at all, at least initially. That meant the aircraft was not relying on symmetry to remain stable. It was designed to tolerate asymmetry. That realization changed everything. Distribution, not power. German heavy bombers relied on paired engines mounted close to the fuselage. When one failed, the remaining engine on that side created a powerful turning moment. Pilots fought the aircraft. Sometimes they won, often they didn't. The British bomber did not fight itself. Its engines were spread farther out along the wing, not clustered, not concentrated, separated. That separation mattered. When one engine failed, the imbalance was smaller. When two failed, it was still manageable, because the thrust was not coming from a single point, but from multiple, evenly spaced sources. The aircraft was not depending on raw power to stay airborne. It was depending on balance. Failure as a design condition. Most aircraft were designed to perform best when everything worked. The British bomber was designed to keep flying when things stopped working. Engine failure was not treated as an emergency scenario. It was treated as an expected state. That philosophy showed up everywhere in the aircraft's behavior. Control responses were predictable. Stability remained intact longer than German pilots expected. The aircraft did not punish crews for damage. It absorbed it. German engineers had assumed the British were compensating after failure. They were wrong. The compensation was already built in. The wing was not an afterthought. The next realization came from wing loading data. The bomber carried more weight per square foot of wing than German equivalents. On paper, this should have made it more dangerous. Higher stall speeds, reduced margins, less forgiveness. But flight reports showed the opposite. The wing was not designed to minimize drag or maximize speed. It was designed to carry uneven forces without translating them into violent motion. Its span, shape, and structural stiffness worked together to smooth out changes that would have torn other aircraft apart. German bombers had wings that demanded precision. The British bomber had a wing that tolerated error. why the engine type mattered, late not early. Only after these pieces were assembled did the analyst return to the engine itself. The engine was not extraordinary because it was powerful. It was extraordinary because it was predictable. It behaved the same way every time. Under load, under damage, over long hours. Across different airframes. The British did not adapt the aircraft to the engine. They adapted the system to the behavior of the engine. That distinction mattered. German designs sought engines that could do more. British designs used engines they understood completely. The final piece. When German intelligence finally mapped the entire system together, engine placement, wing behavior, failure tolerance, control predictability, the contradiction disappeared. Nothing violated physics. Nothing was miraculous. The bomber worked because it was designed around the assumption that things would go wrong. German aircraft assumed perfection. British aircraft assumed damage. Only one of those assumptions survived prolonged war. Transition to consequences. By the time this logic became clear, it was already too late. The bomber had been in service for years. Its crews trusted it, its designers understood it. Its limitations were known and exploited. German doctrine had no equivalent response. Not because they lacked intelligence, but because they had optimized for a different kind of war. Once the logic was understood, the aircraft stopped being treated as a machine with limits. It became a tool that could be pushed. British planners had learned something critical. The bomber did not fail gracefully at its margins. It failed abruptly, only after absorbing punishment far beyond what its designers had originally intended. That made it ideal for tasks no other aircraft could attempt. In 1944, Engineer Barnes proposed a weapon that most officers dismissed immediately. A single bomb weighing more than 10 tons. Not multiple bombs. Not a cluster. One weapon. Dropped from altitude. Designed to penetrate the ground before detonating. The goal was not blast damage. It was structural collapse. Railway viaducts. Concrete bunkers. Subterranean facilities. Targets immune to conventional bombing. The problem was obvious. No operational aircraft in the Royal Air Force could carry such a weapon. On paper, the bomber's published limits said it was impossible. The bomb bay was too small. The landing gear was not rated for the weight. The wings would experience stresses well beyond safe margins. But paper limits were based on ideal conditions. The aircraft had already proven it could survive non-ideal ones. So they modified it. Turrets were removed, armor plating stripped out, bomb bay doors cut open and reinforced. Structural members strengthened where possible and left untouched where the system had already demonstrated tolerance. The aircraft became something new, not a standard bomber, but a specialized platform built to test how far the original design could be stretched. On March 14, 1945, a modified aircraft lifted off carrying a weapon heavier than anything the RAF had ever flown. The takeoff was slow. The climb shallow. But it climbed. At altitude, the aircraft behaved as it always had. Stable. Predictable, unremarkable. When the bomb was released, it fell for more than 40 seconds before impact. The target collapsed. The aircraft returned home carrying visible structural deformation. Wing spars showed stress marks. Components had been pushed beyond normal operating limits. But it returned. The system had held. German engineers understood the achievement immediately. They also understood why they could not replicate it. German aircraft design philosophy was built around precision and optimization. Each component was engineered for peak efficiency within a narrow envelope. Performance margins were calculated tightly. Weight was minimized. Redundancy was limited. This approach produced exceptional machines. It also produced fragile systems. When German designers attempted to break their own rules, the results were catastrophic. The HE 177 was the clearest example. To reduce drag and improve speed, it used paired engines, two coupled together to drive a single propeller on each wing. On paper, it was brilliant. Fewer nacelles, less drag, high power output. In reality, it was a fire hazard. Coupled engines generated harmonic vibrations that cracked crankcases. Cooling systems failed. Engine fires became routine. The design could not tolerate deviation from ideal conditions. And war was nothing but deviation. German doctrine demanded engines that matched aircraft roles perfectly. British doctrine accepted engines that worked reliably and built systems around them. That difference mattered. By the time German analysts fully understood the bomber's design philosophy, production realities made imitation impossible. New engines could not be developed fast enough. New airframes could not be tested thoroughly enough. There was no margin left to gamble on unproven systems. The war had moved on. Epilogue: the MISSED assumption. After the war, German engineers studying Allied aircraft reached a quiet conclusion. The bomber had never been miraculous. It had been honest. It assumed engines would fail. It assumed crews would be tired. It assumed damage was inevitable. German aircraft assumed excellence. British aircraft assumed reality. One philosophy collapses under pressure. The other absorbs it. That was the difference German engineers saw too late, standing in frozen fields beside wreckage that should not have been able to fly. If this story changed how you think about wartime engineering, subscribe. Here we look at the moments when doctrine failed and reality won.